So in this fourth episode, we'll take a look at some actual CAN problems. Before we do, I have one more small piece of theory that I need to go over, and that is CAN voltages. So if with the oscilloscope, I can add basically with the measurements. I'm going to take CAN high, and I'm going to add the mean. The mean is is another word for the word average. I'm going to do the same thing for CAN low. We'll go ahead and add a measurement for it, CAN low, and I'm going to add the mean. And you can see that I've got very close. That's 5 thousandths of a volt away from 4 thousandths of a volt away from being 2.5 volts. This is to whatever it is, 6-7 thousandths of a volt away from 2.5 volts, virtually 2.5 volts within the measurement accuracy of the equipment. So basically, we're looking both CAN high and CAN low at 2.5 volts. I do not have any messages being transmitted right now, so I don't even have my one message per second. I'll go ahead and start the one message per second. We'll take a look at it. And when we see it come up, there we go. It changed my CAN voltage ever so slightly, not by much, just by a little bit. The reason for that is as you'll see as I start adding messages, what I'm measuring is the average. So I want to see the average of this, and we'll go ahead and zoom in on it. I want the average of this entire waveform. So the majority of the time it's sitting in a recessive state. It's sitting in the idle state. It's at 2.5 volts when it's in the idle state, both CAN high and CAN low. When I put some voltage on here, CAN high goes up, CAN low goes down, CAN high goes up to, where do we go, to about 4 volts, 3.8 something. CAN low drops for a peak down to whatever, about 1.15, close to 1.2 volts. So once I average this out over this entire 50 milliseconds per division time frame, we can see that I've got an average of about 2.5 volts. Didn't change it by much. However, if I start to change the cycle time, so I'm going to take the cycle time and I'm going to start to add more messages. And as I start adding more messages, what I'm going to see with the CAN voltages, CAN high is going to get larger and CAN low is going to get smaller. So here I am now. What do I have? I have about 10 milliseconds per 10 thousandths of a second per message. So we can see that CAN high is now a little more than 2.5, CAN low is a little less than 2.5. This is still a very lightly loaded CAN bus. There's not much on here. This has a bus loading of about 6 or 7%. In other words, if we zoom in on this, the majority of the time, 94% of the time, nothing is being transmitted, only 6% of the time. But you can see what it's done with our average voltage. So if I go ahead and I'm going to change the cycle rate, I'm going to go ahead and increase it up to where we're about 50% bus loaded. So here is 50 or 60% bus loading. We can see what that's done with CAN high and with CAN low. They are very close to, it's getting closer to that peak voltage. So as I load the CAN bus, more and more the CAN bus gets loaded. You can tell that it's loaded more. We can see that there's only about half the time that it's idle where I could put messages there. With the bus loaded, the more loaded it is, the more these values go away from the 2.5 volt value. This is the reason why if you look at a CAN bus that's got a problem and nothing's communicating, it's both sitting at 2.5 volts. On a CAN bus, this is more typically what you would measure for voltages, would be something near this 3 volts and 2 volts. So this is the reason that we get that. You might notice that while the data is, while you're running, you have the engine running or something, you're going to see these voltages change oftentimes. These are just sitting here changing by 1,000th or so of a volt. Part of the reason that it does change so much is if I look at this message that I have right now, I'll go ahead and pause. We'll take a look. The majority of the time, it is a dominant bit for the data. So the data is at a dominant bit. If I were to decode this, we know the data is out here someplace. We can see that most of the data is sitting at a dominant state bit, which is representing a value of 0. So just on my virtual engine here, I've got a value of nearly 0 for everything. I'm going to go ahead and just drag this down here. What I'm going to do is I'm going to start changing the data, and you're going to see as the data changes. So this one is sitting here. I'm going to put a value of F in. F is equal to a 1, 1, if you would. So that means that we'll leave we'll set this to FF as well, our torque command. As we do this, we're now going to be changing those dominant bits to recessive bits. And in so doing, you can see that my voltages, my CAN voltages, actually start to change. And this is part of the reason why you can't just look at the voltage and say, within some couple of millivolts or something and say this is the CAN voltage that I expect to see. As you can see, as I'm changing this data, I'm actually changing the value of the voltage. So it's not just a function of the bus loading, it's also a function of what the data is. If I look at the real data now, if we zoom in on some of this, we're going to see that less of my data, I have less of it that is a dominant bit. We can see that there's more recessive bits now, and these are the recessive bits. These are the stuff bits that are stuck in between there. So it's kind of flipped, and we can see that that's changed the voltage. Okay, so what I have displayed here is some actual data that I took in the field earlier this year, back in the spring. This is a Hagie sprayer that has a John Deere Power Systems engine in it. And this is the after treatment bus. So the after treatment bus consists of 2 NOx sensors, a DEF header, which contains the DEF quality and level sensor, and the engine control unit. Something I should mention, John Deere refers to their engine control unit as an ECU. Most of the on-highway guys know that that it's the ECM, the engine control module. Just one thing to note, there are definitely some terminology differences within probably more than just John Deere, the off-road versus on-road. One of those reasons is off-highway is not mandated by EPA OBD in the United States, so there's a service information piece with the on-highway OBD, onboard diagnostics, which requires or specifies that manufacturers must use common industry terminology for the names of components, I think, that are related to emission systems. John Deere is not required to be off-highway, being off-highway, and they're not required to be under OBD, at least not yet. So this is the difference if you have a Cummins engine, even if you're working on a John Deere that has a Cummins engine. Cummins refers to that as an ECM, for engine control module. And this is probably nothing new to anybody who's on highway, but to the John Deere guys, the ECU is something different to them. That means electronic control unit just in general. So one thing with terminology that I wanted to get straight before I get going. But anyways, this is the after treatment bus. It's pretty lightly loaded. If we were to look at this, we would see that it's maybe probably not even 5%, 10% loaded. It is a 250K bus. I'm going to go ahead and zoom in. As you can see, this looks different than what you've seen from what I had on the bench here, because this is actual real data. We can see that there's a little bit of waviness, if you would, here, some oscillations of the 2.5 volts. Part of the reason here to get into this CAN bus, I had to remove one of the terminating resistors, a passive 120 ohm terminating resistor. Had to remove one of those. I put my scope leads where the terminating resistor was, because this data link does not go to the 9-pin diagnostic connector on the machine. This is the after treatment bus. So the rest of the machine is not connected to this, only those after treatment components. So if we look here, we can see a little bit of that waviness, but we really don't care, because the CAN transceivers that are in each of the controllers look at the difference between CAN high and CAN low reference to ground. And if we take that CAN high minus CAN low that I have here, so CAN high being channel A in yellow, I didn't rename it, and channel B being CAN low. If we take channel A from channel B, we can see that we have virtually 0 volts. So even though that noise is there and you see that ripple, you do not see the ripple down here in the what we call this common mode voltage. So because it's the same voltage on CAN high and CAN low, it looks at the difference and we see it as 0. That's why we can look at this. We can look at this message, and even though you may be surprised to think, oh, look at this message, it's got a lot of problems with it. Look at this, it goes up and down, it's got these peaks. This is real data. This is this is what it looks like at times. There's nothing wrong with this data. As we said, we can see the amplitudes of can high minus can low. Even though this is different over here, it's offset, and we can see that. Granted, I didn't sample this super fast. I wasn't really worried about how pretty the waveform was. What I had here was a complaint of intermittently, I would set faults for the NOx sensors missing. So the .09 code for both NOx sensors, which have source addresses of 51 hex and 52 hex respectively. We see our engine controller there with a 0, and then I don't remember what the def header is, but those are the only components that are on this CAN bus. And we can see, as I indicated before, we can see our acknowledge bit. And so on real machines, on real equipment, we can see we've got more than one controller here. So my acknowledge bit has a higher amplitude than any of the others. As I said before, I've had techs tell me, it's like, well, there's a spike at the end of the data. Well, this kind of looks like a spike when I move this out, and you think, oh, there must be some noise there. This is just the acknowledge bit. This is how this works. This is how this functions. You can see this message is a little clearer or a little plainer, but for the decoding piece of CAN and how robust it is, it doesn't matter. It's fine. That variation in voltage, that ripple, really doesn't affect us. So there's our acknowledge bit. We can look at it and see we have 28 microseconds of end of frame data, so we know this is a 250K CAN bus. If I measured the width of this, we would find that the acknowledge bit is 4 microseconds in width in time. Again, go ahead and get rid of my rulers, and we can take our zoom off. And as I said, what I did, I just had the scope hooked up to the machine. The tech had these intermittent problems. As I said, we were setting both 09 codes for the NOx sensors in the ECU. So it was the engine control unit, ECM, was setting the 2.09 codes. It never set the DTC, though, for the def header timeout. Even though there would be a DTC for that, it would not ever set that one. It would only be these two DTCs, and then, of course, the machine would derate, and it was very aggravating for the customer. So this was very intermittent. And so if I were to go ahead and we'll go ahead and add our measurements for, we could do channel A, we'll just say the mean for channel A, which is CAN high, and we'll look at the mean for channel B, which is CAN low. We can see that, as I said, this is very, very lightly loaded. And you know what happens with the voltage when it's lightly loaded. So if you put your meter on here like the tech did, it's like, well, they're both sitting at about 2.5 volts. That's not a problem. This is just a very lightly loaded bus. There could be a lot more components on this after treatment bus, but there's not. In this case, the components themselves were 250K components. And so the machine is 500K. Why don't they just put it on the machine bus? Because you would have to change the components so they're 500K. That would add expense to those. That's some of the reason. So the other part of it is it does minimize how much we put on the other bus, but this isn't that much data. So, but anyways, probably more than anything, the 250K piece of it. So we'll go ahead and go through some of these waveforms. I had this just running live and watching it, and it's like, and I had the tech wiggle the wire harness, and you can see out here something happened, and it's like, what happened right there? Let's see if we can get another waveform where we can see that happen again. Oh, I kind of caught it there. Let's get a better place. Here we are. It's doing it a little more often. Here's a great little example of this problem occurring. If you haven't figured it out yet, what's occurring here is I am driving CAN high and CAN low to almost 0 volts. And so when they're driven at nearly 0 volts, the difference in voltage is still nearly 0 volts, right? 0 minus 0 is 0. 2.5 minus 2.5 is 0. Regardless, I have this problem. I have an intermittent problem. Let's see if we can find it again. Here's my CAN data. And if I look at this CAN data, as we zoom in on it, it's like this controller is trying to transmit, but it can't because both CAN high and CAN low are grounded. In other words, it can't drive into that. It's not able to. It's like a short to ground, right? And so what this ended up being, once again, if I look at my average voltages, granted, I can see now that they're almost 0, but that's just because I'm doing this with the oscilloscope. The very next time they would be this 2.5 volts. So if you were watching this with the meter like the tech did, one thing, it's hard to watch your meter while you wiggle the wire harness around. But if we had a peak hold like a Fluke 88 or a Fluke 87, I might have been able to find this without the oscilloscope. Even with the oscilloscope, it was very obvious what our problem was. This was a very short duration most times. You can see here we're trying to get that message out. The Knox sensor is not able to communicate. We can see that we got this issue. So because of that, because of that short to ground, and what I would have seen on my multimeter if I were just watching it and I had a peak hold, I would have maybe seen it flash briefly. This is not very long that this is shorted to ground. The whole waveform here, 10 milliseconds per division. This is a tenth of a second. It's very, very short in duration. So very long for the engine controller and missing messages from controllers, but this was our issue. Unfortunate for the technician, he had been messing with this for several days, had replaced both Knox sensors, I think even changed the engine controller and maybe the def header. So with the oscilloscope being able to see that waveform and to watch this drop here that we saw, as you can see, this happened quite frequently, but it was very, very short duration that it occurred. We found one particular spot in the harness. He got really lucky and he grabbed right where it was. And when we moved it around, it wasn't a short to the frame of the machine anywhere, the engine block or anything like that. This was a wire to wire short. So within the wire harness, there was the ground for the Knox sensors, and that wire, one of the pieces of copper out of that harness or out of that insulation, had over the years broken, and it pierced its way through the harness. So this machine, I don't know, 5 years old probably, it had actually pierced through the harness, and it's in a location where it's hot, right? It's close to after treatment components, and was able to, if you would, poke its way into the can high or can low. It doesn't really matter which we did with that, which we shorted. In this case, it was probably can high, because of the terminating resistors, as I could explain later. It's basically both are going to go to that same voltage, and we'll see that phenomena in other types of failures. So this seemed like this is a pretty simple failure, and while we needed this very expensive oscilloscope and all this training to be able to find this problem, I would say I would challenge most people to be able to find this on their own. It was one of those things that was like we could wiggle the wire harness around. This duration of the short probably wasn't long enough to set the DTCs. So unless you're watching with a very fast multimeter with peak hold, looking for a problem with the wire harness, and you wouldn't expect that because nowhere was this anywhere near ground. It was actually, it was a section where it was free and it was not connected to anything. So within the loom, this was where our problem was. We took it apart. We were able to pull the wires apart and separate them and get them separated out and wrap some black tape around them for the time being. Ordered that section of harness. I mean, it was pretty cheap. It was a couple $100. It was a fairly simple harness. And then, but in the time being, we were able to get the customer back up and running and then replace that section of harness. So one other thing I should probably mention, I indicated that the complaint on this machine was I was setting the .09, the timeout codes for both of the Knox sensors, so source address 51 and source address 52 in hex. So I didn't set the timeout fault for the def header though, because it's on the same CAN bus. So this becomes one of those things that makes it very confusing. This would be a problem like an intermittent short to ground. You would expect that would cause problems with the def header communication as well, which it would. The difference is the frequency that the messages are transmitted or expected. So the Knox sensors, the engine control unit is going to request those or watch those, get that information from the Knox sensors they're broadcasting, or it may request specific information from the Knox sensors. That information would be broadcast much more frequently. So here you can see this is a tenth of a second in time. And so here I have both Knox sensors communicating more than one time within that tenth of a second. So a brief loss of communication with the Knox sensors for the engine control unit, typically the rule of thumb is if I miss the message by 5 cycles. So if this message is supposed to be broadcast, we'll say we'll just say 100 milliseconds. So every tenth of a second, it's supposed to be broadcast. If that message is missing for 5 cycles or half a second, 500 milliseconds, then there may be a timeout fault that would be set for it. So something like the def header, you can see that it's not even transmitted once. And I looked through all of this data that I had for this machine, for these oscilloscope traces, and I did not have the def header communicate any time at all during that whatever it was, 30 seconds or so that I'm connected to the CAN bus. And so this could be a message easily that is only broadcast, I don't know, maybe once every 30 seconds, maybe once a minute. It's the def fluid level, which we don't expect to change rapidly unless there's a big hole in the tank. But even so, if I got that information at once a minute, that's probably often enough. The same thing for the def quality. It isn't something that we're going to expect to see that quality change, except whenever I fill the def tank, right, or over a long period of time. So that's a message that is not going to be broadcast very often. And so I would have to have my failure in place, in this case, a wire to wire short or a short to ground of CAN high. I would have to have that in place long enough for probably 5 of those messages from the def header to be missing. So that could be several minutes of time. I don't know the exact time for that message, the rate of it. We could easily watch it and disconnect it and see how long it takes for the ECU to set a fault for it. But it's probably going to be in the order of minutes, not in the order of a second or two, like these NOx sensors. So this becomes another piece of the of adding to the difficulty of diagnosing CAN problems on machines. As technicians, you don't know, typically the manufacturer is not going to tell you specifically how long does that message have to be missing before the fault is set. And if you've probably seen this before, where you may have some timeout faults that are set much quicker than others, even though you've got a common problem like an intermittent open of the CAN bus someplace. It's still not all faults set within the same time. So especially intermittent problems, you may set some fault codes with a hair trigger that might set within a few milliseconds. Others may require minutes in order to set if that message is missing. So this is probably enough for this video. This is an example of real data that was taken, and we used the oscilloscope to very quickly get the customer back in the field and get the machine fixed.